Thanks for downloading the In Our Time podcast. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello. If the most famous fruit in physics is an apple, the most famous animal in physics is a cat. It belongs to Edwin Schrödinger, a theoretical physicist who in the early 20th century helped to develop the theories of quantum mechanics. Schrödinger's cat doesn't actually exist. It's the subject of a thought experiment in which the equations of quantum mechanics make it appear both dead and alive at the same time. The problem of a cat that's both dead and alive illustrates the challenges of quantum physics, and at the heart of this apparent absurdity is a thing called the measurement problem. The measurement problem arises because we don't really understand how the particles that constitute our world behave. They're fundamentally mysterious to us, even shocking, and they defy our attempts to measure and make sense of them. Possible solutions range from the existence of multiple realities to the rather more mundane possibility of an error in mathematics, but a solution, if found, could transform our understanding of reality. With me to discuss the measurement problem are Simon Saunders, Professor in the Philosophy of Physics at the University of Oxford, Basil Hiley, Emeritus Professor of Physics at Birkbeck, University of London, and Roger Penrose, Emeritus Rouse Professor of Mathematics at the University of Oxford. Basil Hiley, at the heart of the measurement problem is a distinction between how we think of the world at the level of the very small and how the everyday world of large objects seems to be, classical physics and quantum physics. Can you outline the distinction between the two?
Yes. Let's start, first of all, with the classical world. And one example that I'm going to talk about where we can see Newtonian mechanics actually in action is on the snooker table. We have little balls moving in straight lines. We have balls which we push against the cushion and bounce back again. And we're fairly familiar intuitively with the laws of the macroscopic world. Let's now go down, make the billiard ball smaller and smaller and smaller until we get to the size of an atom. Now let's imagine trying to play snooker with an atom. What we would expect it to do would be to move in straight lines, hit the cushion and bounce back again, and so on, if the laws of Newtonian physics are obeyed. But we get a surprise. If we keep pushing a snooker ball against the cushion, it always comes back again. If we do it with an atom, it sometimes doesn't come back again. It's actually gone through the cushion. And this is the example of radioactivity. But there are more surprises. And I want to bring the surprise out by doing a crazy type of experiment on the snooker table first. Suppose we put two slits across the middle of the table and we push the ball through and notice where it comes from, where it goes to rather, on the cushion at the other end. What we'll find is if we do this at random, that we'll get two distributions with particles arriving at the cushion, and these are two lumps, if you like. Now, when we do the atoms, we would expect exactly the same behaviour. But to our surprise, we don't see that at all. What we see instead of these two lumps are what looks like a set of interference fringes. In other words, there are now places on the screen where the atoms will not go. So, how do we explain this? If we shut one of the slits up, what we find is that it looks almost like the classical picture again. So the important thing is when the two slits are open. The question then is, why does the atom, if it's behaving like a snooker ball, when it goes through one slit, knows the other slit is open or knows the other slit is closed?
Can we just go back to classical physics again for one moment, Basil Hiley, before we move on? And that is that we're talking about measurement in time and space. So if we see, let's take a planet at a certain time, we can say that's where it is, and a certain time later it's much the same planet in much the same universe, but we know how it's moved and why it's moved, and there it is. And that is a certainty which has been worked out by people, by Newton and others up to Einstein, and that we can, well, it's certainly at the moment, that's the rules that obtain at the moment. That is, and these rules do not obtain in the world of particles, atoms, as you say.
In the world of atoms, yes, that's the whole point. it's behaving very differently from what we'd expect on your planetary model and on the game of snooker that I'm illustrating it.
I introduced the name of Schrödinger in the introduction, and he conducted an experiment with a cat, which might be a useful illustration at this stage as to what happens in what could be called the quantum world, which seems to contradict what's happening in the world that we live in around this table and people listening to radios and so on.
Yes, I understand. I wonder if I can, just before I come to that, I wonder if I can continue with this two-slit experiment, because
I think we're going to come to that, honestly.
Okay.
I would just like to get the Schrödinger's cat in and then move along.
Well, the Schrödinger's cat, the problem raised there is that we find that if we do an experiment like the one I'm suggesting, we find that the cat seems to be in two states. It seems to know which slit is open and which slit is closed. In the particular case of the cat, we actually put it in a box and we put some cyanide in there, and when we trigger that cyanide to break it, we've got a particle outside which goes into a half silvered mirror. That means the probability of the atom going in is 1/2, being reflected is 1/2. If it goes in, then the cat dies. If it doesn't, the cat lives. But the point is, to describe that, we need the wave function, and then we've got two packets going through. We then write the cat as a linear superposition of these two wave functions, and therefore, looking at that, taking the wave function as a description of the state of the cat, we find it is both alive and dead.
So a cat that's alive and dead, and Schrödinger said this proved that this showed the absurdity of transferring what he discovered in the quantum world to what would be called the classical world. Can we come, Simon Saunders, to break down this quantum world in a bit more? What is it like, the quantum world, the world of atoms, which I perhaps mistakenly call particles? What is going on there?
Well, quantum mechanics is full of bizarre, strange, exotic effects. And physicists spend their careers studying those things. At the heart of it, I think, is a kind of system of correlations, if I can use that word, which are quite unlike the kinds of correlations we see at the macroscopic level, at the classical level. And related to this system of correlations is a variety of different effects. One of them, non-locality. There seems to be something inherently non-local to these structures that we find in the micro world.
What do you mean about that? What do you mean by that?
Non-locality, essentially action at a distance, but not the sort of action at a distance we were familiar with in physics in Newton's time. These aren't forces acting across distances. They are not forces mediated by any kind of potential function or force function that we know about. It seems inherent to, if I can use this another word, kinematics in quantum theory, that these correlations persist however far away, however remote from each other microscopic systems are.
But there are simpler things to say, aren't there? I'm sorry to be so simple in this, but just to get us started, I mean, they do behave in bizarre ways, the quantum particles. They can appear in two places at once, they can disappear without trace, they can act differently when we look at them, and faced with options, they can take all the options. And that's not the way that this table behaves, or you behave. So there are that sort of difference.
Yes, of course. I think, though, that what you've just mixed in there with some of these paradoxes or strangeness is what happens at the interface between microscopic and macroscopic. In particular, the business of sudden disappearance or being in two places at once and so forth is an attempt really to understand how one goes from the micro to the macro level.
Because that's the heart of the problem, isn't it? We're all made of the same things that come out of the quantum world, and yet there's a big distinction between the way the quantum world, in fact, behaves and the way the rest of stuff behaves.
Absolutely.
And in logically, in a sense, they shouldn't be.
This is something unlike anything we've seen in physics. Let me put it like this. You've mentioned the word Schrödinger. Basil, you've mentioned wave function. Schrödinger, and won the Nobel Prize for it, discovered a wave equation governing the wave function, which is the basic operating tool of the theoretical physicist
Can
in
you
understanding.
unravel that?
Well, I'll say no more than that, in a sense, it's physics as usual. We're studying fundamental laws. Those fundamental laws take mathematical form, and people spend years and years studying those mathematics. And most of theoretical physics, and indeed experimental particle physics, is devoted to getting right what those laws are. So let me call it the Schrödinger equation. The problem with this equation is it appears that we have to suspend it. It ceases somehow to operate. It has to be curtailed, specifically at the micro-macro interface. And where we encounter that interface, or when we're dealing with it in a structural way, is in experiments.
So there's something that happens between laws obtaining when things are very, very small and laws obtaining, different laws obtaining when things attain a certain size, which could be actually a very small size.
Absolutely, and we don't know...
But that's the interface you're talking about. And then there's a jump, something changes.
Absolutely.
And it's the something that changes, or does it, anyway, we'll talk about that, that is the measurement problem.
Exactly. It almost is as though... Here's one way of putting it. Classical physics operates at the macroscopic level, including the design and structure of the apparatus. You switch the apparatus on, a different law kicks in, you register some final outcome of the experiment, that law ceases to operate, and we're back into the classical domain. Understanding how that can be, that is the measurement problem.
Why is this so important, Roger Penrose?
Well, I think the thing about quantum mechanics, let me just say, I think there are two puzzles at the same time. One is the fact that the laws that govern particles are completely different from our experience. I mean, particles can be in two places at once and so on. They can interfere with themselves and so on. However, those laws make mathematical sense. And the Schrödinger equation is one which tells you how a system evolves according to the quantum laws. Now, the other problem is that those laws that work well at the quantum level, small things if you like, suddenly don't work. I mean, it's the problem you've been raising here. But the thing is that we need two different procedures, and they're inconsistent with each other. One of them is basically the Schrödinger equation, which tells you how the quantum state evolves in time. It's completely deterministic. There's no probabilities, nothing like that. But then there's the other procedure, which is what we do when we make a measurement. And what we do when you make a measurement, you might say, well, your measuring apparatus is only made out of particles too, it's just like everything else. Why doesn't the whole system behave according to the quantum laws? And that's not what we do in quantum mechanics. We switch over, as Simon was saying, we switch over from the laws which seem to operate at the small scale to a different set of laws, which are the laws where the probabilities come in, that's where the uncertainties come in, when you make a measurement. And you might think, why isn't a measuring device simply a big quantum system? So all its particles, all its constituents ought to satisfy the quantum laws. There can be two places at once. Cats can be alive and dead at the same time. We never see that. So the measurement problem, or the measurement paradox, is the question is, why is it that when you have something large, say a measuring device, it doesn't seem to behave in the same way that we successfully apply laws to the quantum mechanics at the quantum level, at small scale level.
There's been talk on the part of Basil and Simon about the wave function. Can you just give us, return us to the wave function and say how important it is that at a certain stage and why that collapses?
Well, you see, the wave function is, roughly speaking, telling you, if you have a single particle, you think of it classically, you think of it having one location and so on. But what the wave function does is it tells you, well, roughly speaking, the probability that it might be in different places is actually more subtle than a probability. It's something which uses numbers which involve the square root of -1 and so on. That's mysterious, but it's not mathematically inconsistent. So you can use these laws at the quantum level, and the Schrödinger equation tells you how the wave function, which is telling you what all these different possibilities are all lumped together, and how they then evolve. But that's where you are led to this paradox of the cat being dead and alive at the same time. So Schrödinger was basically pointing out, with this thought experiment of the cat, he's pointing out, as I see it, he's saying, look, my equation would tell you that you have to consider live and dead cats simultaneously. We don't see that, so there's something wrong. We do deal with it in practice by bringing the other procedure, which is not dealt with by Schrödinger equation, but which is the measurement procedure in quantum mechanics, which converts this wave function, if you like, into probabilities. So it might do this, it might do that, it might do the other thing. But that's the big mystery. How do these superpositions, which you get of different alternatives, convert themselves into one or another or another?
Is part of the problem finding an independent position from which we can measure this?
You mean a position? Not a position in the sort of sense of physically where you are.
No.
No, you mean a sort of point of view.
That's right, like the observer and the observed. Well,
that's the trouble. You have all sorts of different points of view, and I think the three of us here, all three of us, favour different viewpoints when it comes down to it, because we're led into this seeming paradox that if you simply follow what Schrödinger's equation tells us to do, we don't get the right answer. We get these superposed dead and alive cats. That's wrong. You don't see these things. How do you explain what we do see? There is a procedure in quantum mechanics, which is the measurement procedure, but it's just sort of ad hoc, if you like. You've got two things. One is the evolution of the Schrödinger wave function, the Schrödinger equation. The other is what you do when you make a measurement, which is where you turn this into probabilities. And you can't get the second from the first. At least that's what I would maintain. Maybe my colleagues have different views on that.
Let's look at the different the ways this has been interpreted. Basil Hiley, starting with you, and something called the Copenhagen interpretation. Can you tell us about that?
Yes, the big difficulty with quantum mechanics is actually understanding why we have to use this wave function. We have to use it in the sense of solving Schrödinger's equation because it gives us a tremendous amount of information about what is going on in the world, and it's all correct. So we have to take it seriously. But we're talking about particles, we're talking about atoms. And a wave function is something which is spread all over space. And this is the dilemma. How do you compare something that's spread all over the space with something point-like? And I should point out that when we do our measurements, we always see point-like results. We don't see this wave as such. So the question is...
How do you know it's there, then?
Sorry?
How do you measure it's there, then?
We don't measure it's there, we use it in the mathematical algorithm, and it gives us the right answer.
Right.
So now we've got a problem. What is the meaning of this wave function? And that's where the debate really starts, the divergences start.
And what did the Copenhagen interpretation add to this?
The Copenhagen interpretation in the hands of von Neumann actually said, let the wave function be the most complete description of the state of the system. That then leads you to a cat. If it's a state, the cat is alive and dead. Niels Bohr didn't have that. Niels Bohr is supposed to be the father of the Copenhagen interpretation, but a lot of people find him very difficult to follow. Some people even have other comments, as Roger I know has, about the Bohr interpretation. What Niels Bohr said was, the wave function and the Schrödinger equation is just a mathematical algorithm, and we must not try to use it to describe what is going on. He felt that the atomic world was essentially ambiguous and we couldn't actually explain, as we would like to in the snooker ball model that I made, what's going on with the electron.
So it's almost as if particles are having thought experiments in themselves, Roger Penrose. Many thought experiments that led to Schrödinger himself.
Yes.
But this is sometimes called the FAPP explanation, the Copenhagen interpretation. What's that stand for, and what do you think of it?
Well, FAPP was John Bell's slightly derogatory, I think, terminology. You know, it sounds like a silly word, but it stands for all practical purposes. Basically, he was saying, well, okay, we can use this interpretation, and it works for all practical purposes, but it doesn't give us an insight into what's really going on. And I think that's the problem. You can kind of get away with the FAP point of view as long as you don't probe too carefully into what's really going on.
But Basil's explained, I thought very clearly, that this was just very useful, as it were, thought experiment to answer certain problems and say, okay, well, that's it. we have an explanation for how that works. Let's just get on with it.
Well, I think it's...
But that isn't satisfying for you.
It doesn't satisfy me, but it also, I think, you see, there are now experiments where you can basically track the wave function. I mean, you don't do it with an individual system. Your problem is, if you have an individual system and you try to find out what the wave function is doing, you can't do that. But if you repeat the experiment many times, there are ways of probing what the wave function is actually doing in time, and we get the answer, which is just as Schrödinger said. It's much more real, in my view, than Basil was. I'm not sure. That's not saying it's your view, but the view you were actually explaining just now.
I was putting over Niels
exactly.
Bohr's point of view.
That's right. So the Bohr point of view, which is roughly speaking, as you say, to say that the wave function isn't really there. It's just a convenience. We use that in order to calculate the probabilities that experiments would give us. It's not real. However, with, as I say, these weak experiments that can be performed on systems really do seem to point out there is something real about the wave function.
Can we take that on, Simon Saunders? The idea of what's real, that Schrödinger's equation was just a mathematical tool and not a model of reality. Can you address that?
I think it's quite important to understand the context that Bohr was working in anyway, which was a very strange body of mathematics that very few physicists understood. Bohr's response to this was to attempt to interpret not so much equations as experiments. So he was really looking at a much more operational, practical, applied take on the various phenomena that physicists were studying. He himself acknowledged, what these equations really mean, gosh, I don't really know. At the Solvay conference of 27, he more or less said, other people here know better than I. But I'm going to talk about the point of view that seems to follow from the phenomena. So, and that I think was tremendously attractive to physicists. But what's happened, 80 years later, these equations have proved remarkably robust. They seem to deliver. Wherever you apply them, they seem to work. I think what's happened in the physics community, and it's rather typical in physics, that mathematics that is effective, powerful, productive of new ideas and so forth, one lives with this mathematics, one imbibes it, it becomes really the world as seen by the physicist. And I think all working quantum physicists have to treat the wave function seriously. It's the stuff out of which the microscopic is made. I don't think people seriously doubt that. The problem is always, I come back to it, how to understand its relationship to the macroscopic. Now Bohr did have an answer to that. I think it's important to look at it, put it on the table. Ultimately, I think it's got to be put away because it doesn't work. But the answer was this. This strange replacement of a law with another, or suspension of a law, it's to do with some fundamental epistemic condition, epistemology, theory of knowledge, something to do with the relation between the observer and the thing that is known. So some philosophical, long-standing situation that we can't get out of, that's what it's signalling. So it's not a problem for physics. It's somehow just endemic to the human situation.
So when the observer observes, the observed, what is observed, changes because it's being observed, because the observer is part of the same world as the observed. Is that what you're saying?
Indeed, but of course that can seem like a rather trivial point. You poke something, it has an impact on the thing that you poke. So it's got to be, and Bohr tried to couch it in a more fundamental sense, something to do with an epistemic constraint. I mean, Kant had the same thing. The object under an epistemic constraint as an object of knowledge, and then it's a different thing from the thing as it is in itself. So this is a very long tradition in philosophy, and physicists, well, the more philosophically inclined ones anyway, we're happy to see the measurement problem as just a further episode of that, or perhaps a deepening of that. Okay.
Roger Penrose.
I think it's certainly true that Bohr's point of view, although we may think of it as an incomplete or even inconsistent viewpoint, was very important for the development of quantum physics. I think if people had spent the whole time worrying about the foundations, it wouldn't have got anywhere. And Bohr's point of view enabled people to sit back and actually do the physics properly and not worry too much about the deep problems, but they came later in a sense. I also like to make a point about the issue of, measurement involves disturbing the system and so on. it's very curious that there are types of experiments where the non-measurement of something actually has an effect on it. I mean, it's very curious. You might think that the problem is you can't measure something because it's so delicate, and if you tried to, you would disturb it and change it. But there are these things called null measurements, where the non-measurement of something, just the fact that you might have measured it, influences what happens. And this is one of the very strange puzzles in quantum.
We are talking about sort of magic on stage here.
It's almost that, yes.
Yeah. So you're thinking of doing an experiment, and it's in your mind that you're going to do an experiment, and the fact that it's in your mind going to do an experiment...
that's not quite what I mean. You actually have to have an
that's
experiment.
That's what I got, so obviously I got it wrong. So perhaps why don't you have another go?
Well, you have a particle detector, say, you see, and the particle might come one way or it might go another way. And if this detector does not register the particle, so you know that the particle hasn't gone the way that the detector would have detected it gone that way. So therefore you know it has gone the other way. And the fact that it...
I thought you were talking about what was in your mind. I didn't think
it's not in your mind. No, you actually have to have a detector.
Yeah.
And it's the fact that the detector does not register. It does not interact with the system, influences the system.
Can we move to another explanation, Basil Hiley? You work on the Bohm, I hope that pronunciation is correct, the Bohm theory about the relationships between mathematics and the reality, which is what we're talking about. I'm struggling with at the moment. Can you tell us what the Bohm theory is, briefly?
Well, the Bohm theory is essentially taking the wave function seriously, but then arguing that because of the type of situation we get with poor old Schrödinger's cat, there's something missing from the formalism. And the problem is, what is that missing feature? You see, underlying quantum mechanics, something that we haven't talked about yet, is the uncertainty principle. What we find is that we cannot measure position at the same time as we're measuring momentum. So that means that we can say where a particle is, but we don't know how fast it's going. Or we can say how fast it's going, but we don't know where it is. Now,
so all these things are happening inside us, aren't they? Because we're particles. So while you're talking, all the things you're applying to particles are happening inside your body.
But fortunately, I'm macroscopic, and therefore you don't see it. And this is what Simon was saying. Somehow,
you better get to the join quickly, or there'll be panic in the ranks.
Yes.
Never mind. Right.
Okay. So the Bohr's position, von Neumann's position, they said it's not possible to get a more detailed description of what is actually going on, what is behind these measurements. And what Bohm said was, no, there is always an actuality behind appearances. There's an essence behind an appearance. So what we see in our instruments are merely appearances of some deeper essence. Now, can we get some sort of handle on that deeper essence?
What handle did he get?
He got a very simple one. His actual ideas are much more sophisticated, but let's make it simple. That is that the particle actually exists with a position and with a momentum.
So it can be you can see two things at the same time.
No, I'm not seeing them. I'm saying the particle has them. That's the essence.
Has them, yeah.
Okay.
Right.
Now then, the problem is, where in the formalism do we have anything which tells us these two things simultaneously? Because if we're measuring things, they're observables, and they cannot be observed simultaneously, so we cannot give them value simultaneously. But there is another feature in the formalism, which comes technically from the energy momentum density tensor, which is a momentum, and it's that momentum which is different from what we would observe, that we say is the beable for the particle. Given that, and we know how to calculate it, we then find that we can explain all the quantum phenomena and yet have a particle following trajectories in the traditional sense.
There's a homely example, isn't there, that two things can be happening at the same time. Someone can be smiling, and at the same time they can be feeling great grief. So two things can be happening simultaneously. The reality inside is the grief. The exterior is a smile to sort of get through the afternoon or whatever it is.
And of course the exterior is you can only see him being happy, and you can't see him being sad at the same time.
And that reinforces the the theory you've been working on.
Yes,
not reinforces,
it uses that idea.
Yes. What do you make of that, Roger Penrose?
Well, I mean, there are lots of different... I very much respect the Bohm type of view because it actually gives you, as these interpretations do, they're usually pretty unclear about what's real in the world. I mean, the ontology is very obscure, and certainly that's true in the Copenhagen viewpoint. Whereas the Bohm interpretation really attempts to give you a picture of a real world under there, which I'm very sympathetic with. I don't go all the way with the point of view of the Bohm interpretation, if you could call it that. I suppose for a reason that I think that, you see, it's not really revolutionary enough. The Bohm type of point of view doesn't claim to have anything different in its implications from standard quantum mechanics. Whereas, in my opinion, there has to be a level at which standard quantum mechanics will turn out not to be correct. And this will be something that you can see in actual experiments. So it'd be something like a Schrödinger's cat, but you don't have to go that far. But you'd have an experiment where you say you don't have a cat which is alive and dead at the same time, but you have an object, a macroscopic object, which could be maybe just a bit too small to see, perhaps, but just a macroscopic object which is put into two locations at the same time. They're slightly different from each other, and the question is, can that actually persist in time, or does it spontaneously become one or the other? And according to certain points of view, such as the one I favour myself, there would be a time scale beyond which it would not be in two places at once, if you like. It would flop over into one or the other spontaneously. And it's nothing to do with us measuring it or looking at it. It does it itself. And this is different from standard quantum mechanics. And I think it would be different from the Bohm view, because in the Bohm view, you're, in a sense, having a different interpretation of quantum mechanics, a different way of looking at it, which is perhaps superior, and I think perhaps it is, superior point of view with regard to quantum mechanics. But I think you need more than that. You need something where the implications of the theory at a certain level will turn out not to be what the actual world does.
Just a footnote, Basil, then I've got to go to Simon.
Yes, sure. Just to clarify Bohm's position on this, I said it was a simple model, and it was a simple model to begin with, but what he was doing there was to show that a simple model of the underlying reality was possible. But we need to modify it, and that's where the new experiments might come in.
Yes, no, it's fine.
Simon Saunders.
Yeah, just to make a point, I don't think it's right to say the pilot wave theory is an interpretation of quantum mechanics. It adds new elements. There are new equations. And one really has a different theory. And indeed, that theory may well make different predictions from standard quantum mechanics, depending on just how those add-ons go, specifically to do with the probability interpretation, in fact. This is the sort of thing Valentini works on, non-equilibrium, pilot wave theory, and so forth. But look, I think there's a fairly straightforward trilemma, really. What we're dealing with is one equation which seems to be suspended or changed, the collapse of the wave function. How to go with this? One way is to model it dynamically, which is more or less what Roger is saying. There are theories on the table already of that form. In principle, they can be empirically distinguished from standard quantum mechanics. We can hope for testable resolution here. Roger's own view is that gravity plays a fundamental part in that, and it seems to me that's extremely exciting. And in some ways, it's the serious way to go as a working physicist. I say that because working physicists at the fundamental level are concerned with how to relate quantum theory to gravity. It's the holy grail, as it were, of contemporary theoretical physics. The pilot wave theory doesn't collapse the wave function. And it's rather remarkable how nevertheless it creates or will account for the appearance of collapse of the wave function, essentially through a sort of an irrelevance. Most of the wave function becomes irrelevant with respect to what Basil's been calling the beable, these trajectories. The wave function dynamically determines how the trajectories go, but large regions of the wave function cease to be relevant to that. If you like, they're too far away. So that's a way to go. And the problem with both ways to go is we really don't know how to do this in the relativistic domain. We do know how to do it in the non-relativistic case. We don't know how to do it in the relativistic case. And we seem to be in this bizarre situation, taking seriously either of these two proposals, that we've somehow got to do particle physics all over again. 50, 60 years of work with thousands of physicists, cooperative work, all those Nobel Prizes that were awarded and so forth. Well, we've got to do it all over again. That just seems insane. This just doesn't happen in physics. So this is, in a way, the very strange situation that we're in. We know how to solve the measurement problem, but the community of physicists have voted with their feet otherwise.
You want to say something?
I just wanted to pick up one point there, and that was over the fact that traditionally it's always believed that you cannot do the Bohm theory with relativity. In the last 3 or 4 years, I have been able to show that you can do the relativistic Bohm theory. And okay,
No, then Roger wants to come in.
I just want to comment that the fact that we have to do physics all over again is no argument against. I mean, I would point out that this has happened before.
Oh.
It's not unprecedented.
Yeah.
It happened with Einstein's general theory of relativity. We have a completely different viewpoint with regard to space and time. And you might say, don't we have to do all of physics all over again? Well, we do, strictly speaking. But at least Einstein's theory, first of all, there are approximations where you can get away with using Newtonian theory most of the time. But it's really a completely different outlook. And it tells us that gravity is not a force in the ordinary sense of the word, and so on. And I think we are looking towards a revolution of that kind.
Yes.
It has to be something which does overthrow all of our standard views about particles and so on. It may not affect what people do in detail.
I'm all for revolutions in physics, but one expects new phenomena. And they are typically in reaction to new or well-known anomalies. The situation in quantum mechanics is we don't have that. We don't have new phenomena or anomalies. We do have the problem of how to reconcile quantum theory with gravity.
I think the trouble is that we haven't done the experiments of the kind which would probe this, and that involves mass displacements.
Right.
None of the experiments in quantum mechanics get close to the level.
Absolutely. No, these are important experiments, no question.
Can I just move on one more step before we go? Basil Hiley, there's another solution which says that Schrödinger's equation is a complete description of reality, and that's what it is, and the wave function does not collapse, and there's a many-worlds solution to this. Could you explain to our listeners what that is?
You're asking me, but I think the real person you should be asking that question is Simon, because he has studied it in great detail. And
Simon, over
I'd
to
like
you.
to hear Simon's.
Well, okay. The many worlds interpretation was first put on the table 50 years ago by someone called Hugh Everett. It was crazy.
Can you just explain briefly? Not
why it's crazy. How it's crazy.
Just explain what it is. Yes.
Yeah, indeed. It's the view that the wave function indeed never collapses. What we see is only one part of the wave function. Other regions of the wave function also have equal reality, equal validity, and there they are, people just like us, arguing, debating. Perhaps there's Saunders who missed his taxi this morning, failed to show up, goodness gracious, the whole show was about pilot wave theory and gravitational collapse. Many worlds didn't get a look in. That's also there in the wave function.
In other words, that these things do take every option. Particles, atoms do take every option, and so there's every possible world coexisting at the same time. So there are billions and billions and billions and billions of worlds at this moment, which proves Schrödinger's theory. And that is one way to say, yes, this is fine, we'll carry this right through, and that's what it ends up at, the many worlds. And that has a logic to it, and it follows the mathematics, but it seems, Roger Penrose, to you, to not make much sense.
Well, there are two levels at which I think it doesn't. One is, of course, it's a crazy theory, but of course that shouldn't in itself be a reason against it, as we know. But I think the problem with it is what you really need, it's not really finished in my view. I mean, okay, maybe all these different worlds do exist simultaneously. The cat is alive and dead in two separate worlds, if you like. When you look at the cat, then
actually it becomes billions of worlds. If you
it's
follow
more.
it through,
Well, let's not worry about how many it is. If you look at the cat, there's one of you who sees the dead cat, and another copy of you in the other world which sees the live cat, and so on. I think the trouble really with it is not its craziness, but that it's not a completed theory, because you need one of two things. either a theory of real physical behaviour, which this is not, you see. It's telling you the world that we seem to see is not, I mean, it's there and the other worlds are there at the same time. But if we don't have a theory of real physical behaviour which actually mirrors what we see, that is to say cats are either alive or dead, but it has to be therefore a theory of experience. The theory has to tell us why a person like you or me would only see a live cat and not a superposition of live and dead cat. Why doesn't experience allow you to perceive this superposition of different worlds? And what we only see is one world. So you need a theory which somehow it gives us that.
Yeah. There's a very long history of introducing questions of consciousness, the mind, into quantum physics and the problem of measurement. I think there was a time when the many worlds interpretation was susceptible to this kind of criticism, but I think the way it's been developed over the last 20 years or so, it's the wrong objection to make, because what the claim is, and this is really my own interest in many worlds, take the Schrödinger equation, study it for complex structures, and use just standard methodology in the special sciences to extract from it interesting structures, interesting high-level emergent phenomena. And the claim on the table is that doing that you do see in the wave function macroscopic, stable things, objects, cats, people, chairs, tables. You see all of that stuff. It's there in the physics. And it's there in a way such that they can't couple with one another. These things are dynamically disassociated from one another. Now, if you've got all of that, if you've got the chemistry right, decoupled in one region of the wave function from the other, if you've got the molecular physics right, you can get all of the rest out later.
Thank you. Later is the word, I'm afraid. Thank you very much, Simon Saunders, Basil Hiley, Roger Penrose. Next week we'll be talking about the library at Alexandria, founded in the 3rd century BC. Thanks for listening.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.